Alrighty, back with some mental fun gymnastics to do with these potentials. The statement reads, for part A, construct a scalar potential U of R for a pure magnetic dipole M. B, construct a scalar potential for a spinning spherical shell. And C, try doing the same for the interior of a solid spinning sphere. Alright, so for this solution, let's consider the analogy with the electrical case, where we have E in terms of the coordinate-free form with the dipole, 1 over 4 pi epsilon naught times 1 over r cubed, bracket 3, p dot r hat minus p, and we know that E is equal to the negative gradient of V, where V is the potential of 1 over 4 pi epsilon naught p dot r hat over r squared. With the magnetic version, which we given the field, and we know that the suspected scalar potential exists, it would take a similar form. So we say that U is equal to mu naught over 4 pi m, the magnetic dipole, times r hat divided by r squared. Evidently, the prescription here for the analogy is P over epsilon naught goes to mu naught m. All right, fair enough. Part B. The comparison/direct calculation shows that the dipole moment of the shell is m equal 4 pi over 3 omega sigma r to the fourth z hat. And from A, the scalar potential would then be mu naught omega sigma r to the fourth over 3 cosine theta r squared for r, little r greater than big R inside the shell. Whew. And the field is uniform, B equal 2/3 mu naught omega sigma r z hat. So U equals the negative 2/3 mu naught omega sigma r z plus C. And we may as well pick any constant C, right? So we just set that equal to 0. And we see that the potential for inside, or little r less than big R, is 2/3 mu naught omega sigma r little r cosine theta. Good to go. For part C, we see that B has to be the negative gradient of U. So just plug that away. Have fun with that. We see that the magnetic field is equal to this first term in the brackets. And we know that the negative gradient can be expanded term by term like that. So if we compare this component-wise, we can see that we have negative 1 over r sine theta du d phi hat. We don't have any components to compare it to, so it has to equal 0. So we set that equal to 0, get rid of all the constants and such, and solve away. So we know that u is equal to a function of r and theta, not of r theta phi. Similarly, we compare for the theta component, and we solve through for that to get a function of u of theta. Now remember that when we solve through, instead of a constant, we get a constant function, meaning it's a function of the other variable. So we have to account for that, and we do that similarly for the radial direction. Now we need to exploit these two, and we see that by equating them, we'll get an expression for g of theta, and that's equal to some constants here times r cubed cosine plus the radial constant function. But there's no way to write r cubed cosine theta as a sum of functions of theta and of r, so we're stuck. The reason that you can't have a scalar magnetic potential in a region where the current is non-zero. That's quite a bit of mess, ain't it?